Hi, hi. Yep. Hi guys, my name is Samuel Jasper. I am from CSC department. My topic for AIT for mathematics for computing is on binary multiplier circuit. Let's get into introduction on what is binary multiple circuit is all about. A binary multiplier circuit is a combinational logic circuit designed to perform multiplication of two binary numbers. A binary number consists of only two numbers. One is zero and the other is one. When you write a zero, when you write uh, one beside a zero or a zero beside a one, the that thing is known as a binary number. So when you perform multiplication on two numbers, then we can there is a result in a binary multiplier circuit. That is what it is. It follows the same principle as decimal multiplication, but uses binary arithmetic zeros and ones, like as I said before. The circuit generates partial products using AND gates and then adds them using adders to obtain the final product. So we use AND gates, and with the help of AND gates, we add them, and the adder goes, and the adder results in the final product. Binary multipliers are widely used in the digital system, such as microprocessors, arithmetic logic units, digital signal processors, and etc. They are essential for performing fast and efficient arithmetic operations in a modern computing devices. The object. The main objective of this topic, binary multiplier circuit study, is to understand how binary multiplication is done and how binary numbers are multiplied using logic gates. To learn how partial products are generated and combined. To study the working principle of a 2-bit and a 4-bit binary multiplier so that we can create our own processor and supercomputer and etc. and many other things. To explore the applications of binary multipliers in digital electronics and to understand how multiplication is implemented in computer hardware. Binary multiplication basics. Okay, binary multiplication is similar to decimal multiplication. See, like in normal multiplication, we multiply using tables. Like, let's say you have 2, 3 into 2, 1, 5 into 5. Then we multiplied 5 with 5. We get the answer and we carry when there is an extra and we multiply with the 5 into 2. So when we get the product, we add the adder and we get the final product. In the same way, we have the binary multiplication basis where we need to learn the basics to in order to do a binary multiplication. So let's get into it. Binary multiplication is similar to decimal multiplication but uses only zeros and ones. In normal multiplication, we use every single table, but here it's not that way. We use something like few logic gates such as AND gate, NOR gate, OR gate, and many other gates. So with those gates, we perform the binary multiplication depending on the condition it need to satisfy. Okay. Each bit of the multiplier is used to generate a partial product. These partial products are then shifted and added to get the final product. So this shift method and the add method are used to form a binary number in programming. It is very essential and very useful. Without this, to form a binary number, it's very difficult. Though it is easy, but it's very this is very comfortable in order to form a binary number. Logic gates such as AND are used to generate partial product. So in AND gate, what happens is you need to have two ones in order to get a one, and you need to have two zeros in order to get a zero. If one number is zero and the other one is one, you the product you get is zero, and this and the vice versa. Adders, half and full adders are used to combine them. So like as I said before, this is binary multiplication. So 2 in decimal and 3 in decimal. So you need to multiply 1 into 0, you get the 0, and 1 into 1. So both are true. So you get the product 1. In the same way, you multiply 1 with 0. So both are not same. So you get the product as 0. And both are 1s. So you get the 1 and the whole product, you get 110. Consider two binary numbers. Multiplication and A is equal to A1 A0. Multiplier B B1 B0. The binary multiplier product produces four partial products using AND gates A0 B0, A0 B1, A1 B0, A1 B1. These partial products are added using full, half and full adders to get a 4-bit product. So the output we get are P3, P2, P1, P0. Logic diagram. A two-binary multiplier circuit uses AND gates to create partial products and adders to combine them. The structure shows how each bit of the multiplication and multiplier interacts to logic gates. So, like as I said before, only through the foundation of the logic gates, everything is done. Either it be everything is done for an arithmetic operation. For example, I'll explain you and then let's get back to the explanation. Each AND gate generates a partial product. A naught B naught, A naught B1, A1 B naught, A1 B1. So in multiplication, when only when two numbers are merged or multiplied, only then we get a product on a single product. So like in the same way, A naught B naught. If both are true, we get true. If both are false, we get the false, and the same is applied to the rest of the things that are behind it. Step 2. The partial products are connected to half adders and full adders. The adder outputs form the final 4-bit results. So with the use of the half adder and the full adder, we get the final 4-bit results such as P3, P2, P1, P0. So this is the half adder and the full adder. So A1 goes to HA. This is the AND gate using the A1. With the help of AND gate, P2 is formed from P to H and P1. The same way, A0 and with the help of AND, P0 with the help of A1, we again get A0 P1 and the same vice versa. So here's the truth table for the A1, A0, B1, B0 and the full and half adder outputs P3, P2, P1, P0. So when you combine when let's I'll tell you A1 A dot 0 0, so I get 0. uh, so both are 0, both are false, both are false, so I get false. A1 A not 0 1, so one is true, one is false, so false. False, true, false, false, true, false, false to false, false to false, false to false. In the same way, A1 A naught follows the P3 one. So at the end of the A1 and A naught, we have both true. So when both are true, we get the true output. So in the P3, we have the true output. In the same way, A naught B1. So false, 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 true, false, false, true, true, true. True, true, true. False, true, false. False, true, false. True, true, true. True, false. True, true, false. So this is how it goes. It is very easy, but at the same time, we need to look after the multiplication, such as we have the condition, like as I've said before, only when the one statement is true and the other statement is true, then we have the true product. If one of the statement is false and the other is true, or else if the one is false and the other is true, we get the product as false. No matter what it is, no matter how true the statement is, how strong the statement is. If one is false and one is true, then the result we get is false. If both are true, irrespective of the strong statement, it is always true with respect to the and gates methodology. Types. Based on the bit size, we have uh, you know, two types. One is dependent on the bit size, and the other is on design techniques. Like on the bit size, we have 2-bit and 4-bit, and 8-bit and 16-bit. So in 2-bit, the design is we use is using AND gates and adders. In 4-bit, the which is an extent of 2-bit logic and more and of full adders. 8-bit and 16-bit multipliers uses used in processor for larger computation. So let's now get into based on design techniques. So in design techniques, we have array multiplier, booth multiplier, Wallach tree multiplier, sequential multiplier, and etc. So in array multiplier, we use a grid of an AND gates and adders. In booth multiplier, we handle signed numbers efficiently with Booth's algorithm. Wallace tree multiply. We use parallel adders for high-speed operation, and at the same time, the last we have sequential multiplier, where we use shift registers, slower but hardware efficient. Advantages and disadvantages. We have a lot of advantages through this binary multiplication, and at the same way, we have a few disadvantages, but the advantages stand out with respect to the disadvantages. So let's get into the advantages. Advantages: we perform fast binary multiplication in hardware. So in our chips, so the processor which is in your mobile or in your PC or in your laptop, the binary multiplication is done very fast, extremely fast. So with that, the process or any task or any instruction that is given can be implemented faster without any interruption, without any time delay, so that our work gets done in time. Simple design for small bit width operation like 2-bit or 4-bit. Easily implemented, like as I said, easily implemented and easily done without any time delay. Forms a core of ALU and processor for arithmetic operation. The same is applied for any operation, like take any operator such as addition, multiplication, division, subtraction, XOR, multiplication, anything. Everything is applied in the same way. Suitable for digital signal processing (DSP) application. So this digital signal processing, why it is applicable or why it is suitable, the because binary multiplication, like as I've said, it is very extremely fast, and the task is done and the instruction is implemented and conducted very fastly. So in order to transmit the signal from one place to another place, you need to be fast and you need to be transfer the signal so extremely fast. So the signal digital signal processing is suitable for this binary multiplication. So the disadvantages: hardware complexity increases the number of bit, grows power consumption, rises for large multipliers, propagation delay occurs due to multiple adder stages. Application: we have so many applications such as arithmetic logic units, DSPs, microprocessors, microcontrollers, embedded systems, computer graphics, cryptography. Conclusion: the binary multiplier circuit is a vital role of digital electronics that enables efficient multiplication of binary numbers. It uses AND gates for generating partial products and adders to sum them up, producing the final output. Understanding binary multiplier helps in designing faster and more accurate and more faster, more efficient computing systems. Thank you.